this last video, we look at 3 ways to decrypt the files corrupted by the ransomware. The first method that we'll use is based on an observation that we made in the previous video. We saw a string that mentioned that the files were decrypted successfully. If we go back to see where this string is being referenced, it is only referenced in one function, this one. We can look at what the function does. It's quite straightforward. If we check where this function is being called, also only in one place. Though, notice that just before this function is executed, there is a comparison between two strings. The first comes from the encrypted data section. It was previously encrypted, but now its value is here. The second string comes from the getDLGItemTextA function, which reads input from the user. If they are equal, files will be decrypted automatically. Practically, this means that at the end of the execution, the sample will present a dialog box asking us for a password. We will need to provide it the correct one that matches the static string. But that was too simple. Let's find another way to get the files back. Go back to second encryption function that we've renamed as encryption2 and see what it does. We've already established that it's the XDA algorithm. We'll download the Python implementation of this algorithm and modify it a bit to match our sample. You don't need coding experience here, but please look at the code and follow through. Or even try to play with the script. Here is a standard code for XT algorithm, key setup, encrypt decrypt blocks, and so on. We wrote a wrapper around these functions to either encrypt or decrypt any text. Very important here, we need to supply the key. Block length is 8 and the key length is 16. But where does the key come from? Remember, in this function we saw 4 constants that were initially not defined. Each one is 4 bytes, in total 16. We don't have their values just yet. They represent the key and their values will be visible at runtime. Run the sample and check. We'll set up a breakpoint before this call, then run the code. This is actually the interesting function we've seen in the previous video. Run until the anti-virtualization check. Then patch the value of AL register to 39 and the execution can now continue. Let's go back to our function named encryption2. We now have the values for all the parts of the key. Exactly what we put in the script. We'll test it against an already encrypted file. This one, for example. Okay. Let's see if we can get the original image back. Run the script, specify decrypt, and pass the path to the encrypted file. It should produce another file containing the expected image here. This was the second way to decrypt files, based on a Python script to decrypt XT. Another interesting option is to take the code out of IDA-Pro. We could actually decompile this assembly code straight into C source code. Unfortunately, the decompiler plugin is not present in the free version of IDA, so you either need the commercial version or a different decompiler. This is outside the scope of this course. A source code and compiled binary are provided in the resources section. The logic is exactly the same. Same functions. This code corresponds to the long function we saw here in assembly code. Let's see what happens if we compile the source code and run the executable. We have already the code compiled here. Okay. We run it against the same encrypted image file as before. It will produce an output file, which we will rename to JPEG. And again, same decrypted file. Now you have three methods to recover the files encrypted by this ransomware, including a very simple one, which doesn't require any coding at all. And also one Python and one C implementation of the algorithm. Thank you very much for watching, and I hope you will practice these techniques on your own and try to reproduce both of the decryption routines. Thank you!